Okay, that is everyone for now. So I will already start with the introduction. Again, welcome everyone. As you can see on the screen, today we are joined by Peter Bishop from Harvard University in the USA, who is going to talk about the makings of a mammal, insights from the fossil record, and computer simulation. So the format of today's seminar, if you're new here or you haven't been here in a while, we'll first do the welcome and announcements, which is what I'm doing right now. Then we'll have Peter's talk for around 30 minutes, followed by a moderated Q&A for around 10 minutes. You can send your questions already during the talk to our questions at Paleoperk's host, who today is Salman. And after that, Peter has agreed to stay for tea time. So if you want to have a chat in a more informal setting, or if you want to ask some technical or difficult questions to him in person, then you are free to stay afterwards. So then a bit of housekeeping about Paleoperks. So Paleoperks values the participation of all folks interested in the paleosciences. For that, please remember to abide by our code of conduct in today's seminar, which you should have read if you are able to access this seminar. Also, please keep yourself muted today for the talk out of respect to today's speaker. You should be muted for the talk, but if you find yourself unmuted, please mute yourself again. As I mentioned earlier, you can ask questions by chatting to the questions at Paleoperk's host. You can also use the raise hand function if you would like to ask the question yourself. And if you experience any technical issues during the talk, you can also shoot them to Salman at the questions at Paleoperk's host. Then we also have closed captions built into Zoom, and you can use the CC button to either show or hide them. And finally, this seminar is run, well, it's run by us, but it can only run because we have so many great early career speakers that want to give a talk and share their work. So if you know a cool early career researcher or you are one yourself, you can also nominate yourself, then please go to this link. It will be dropped in the chat shortly. And then finally, we also have weekly feedback forms for demographic information. It's completely anonymous and optional, but we would really like it so we can continue to improve this seminar series. And this will also be dropped in the chat. And then a final announcement, we are looking to for some people to join our Paleoperk steering committee by the end of this year or start of next year. We're specifically looking for people who are interested in social media and funding outreach. However, we are doing a lot of tasks behind the scenes, and if you're willing to devote some time for service to your paleo community and also learn some cool skills and meet some cool people, you are welcome to apply. You can find the link on the website. Application is open till November 10, and you can also find it via this link that you see on the screen. And we look forward to hearing from you. And with that out of the way, a bit more information about the speaker, Peter Bishop. Peter did his Bachelor of Applied Sciences in Geosciences in the Queensland University of Technology in Australia, followed by a PhD in biomechanics at Griffith University, also in Australia. He then went on to do several postdocs, one at Griffith University, one at the University of the Sunshine Coast, also in Australia, and finally one at the Royal Veterinary College in the UK. Currently, he's a research fellow at the Museum of Comparative Zoology at Harvard University in the US, as well as being a long-term adjunct research associate at the Queensland Museum in Australia. And with that, Peter, I would like to invite you to share your screen and start your talk.
Thank you very much, Leah. So hopefully everyone can see my PowerPoint presentation.
Yeah, looks great.
Excellent. Okay, well, thank you very much for having me today. It's a great pleasure, a great honor to be invited to present to you all. So hopefully we'll all learn something about how mammals came to be and have a bit of fun along the way. So first of all, I would just like to acknowledge and pay thanks to the many, many people and the many institutions that have supported the research that I'm going to be presenting to you today. In particular, the museum curatorial and collection staff from museums all around the world that have facilitated my access to the fossils in their care. Quite simply, without their help and without these people, our field would come to a grinding halt. I'd also like to make special mention of my main collaborator, Professor Stephanie Pearce at Harvard University. The work that I'm going to be presenting to you today is as much her work as it is my own. Okay, so modern mammals, they're very distinctive. We all recognize them today. They're highly diverse, very successful, they're everywhere, and they're characterized by a whole suite of anatomical and physiological traits that set them apart from every other group of animal that we have with us today. And so I've got up on the screen here a few of the more conspicuous of these traits. So they've got complex dentition and they're feeding, so they chew their food. Their integuments, the hair or fur that protects them and keeps them warm. Transformation of the bones in the lower jaw to become the little tiny ossicles of the middle ear for an enhanced hearing. Mammals produce milk for their young, and they often show extended periods of parental care. Mammals have a very complex and differentiated or regionalized vertebral column, which allows them to do a whole range of different behaviors. And mammals have also evolved this novel muscle in the thoracic cavity, the diaphragm, which enhances with breathing. One other distinctive aspect that characterizes modern mammals today is their many and diverse ways of moving around their environment. You name it, you think of it, they probably have done it or still do it today. So they walk, they run, they fly, they hop, they jump, they swim, they dig. Some mammals have even gone into space. Now, this has allowed mammals to radiate and colonize pretty much every environment on Earth today. And underpinning this great diversity in locomotor behaviour was a major shift in the way that the extinct ancestors of mammals stood and moved. And this can be broadly encapsulated as a shift in limb posture from a sprawled limb posture, where the limbs are held out to the side of the body, kind of like a lizard or a salamander, through to the erect posture that we see in modern placentals and marsupials, where the limbs are held underneath the body. Now, in tandem with these shifts in posture, we also see major changes in the muscular and skeletal anatomy of the limbs and the vertebral column, so that the anatomy of modern mammals is very distinctive from that of other animal groups as well. And so we're forced to ask questions like, how did this come about and when did this come about? What were the patterns and the processes by which all these major transformations in anatomy and function, how do they all come together to create this new, radically different body plan that characterizes mammals? And perhaps more broadly, what were the major and overall driving factors or selective factors that led to these massive shifts occurring in the first place? Now, these kinds of questions pertain to patterns and processes that occurred long ago over deep time, and so we need to go to the fossil record in search of answers. And so in this talk today, I'm going to break it up into two parts. Firstly, we're going to look at how we can better reconstruct and understand how the distinctive muscular anatomy of modern mammals came to be. And that involves reconstructing limb musculature in extinct species, which in turn has important implications for our understanding of what these animals look like as living animals. And then in part two of this talk, with our improved understanding of limb muscle anatomy, we're going to use biomechanical models and computational approaches to probe and quantitatively test and explore questions about limb posture and locomotor function. And again, using that to better understand how this has changed over millions of years on the line to modern mammals. But first, I just want to bring everyone up to speed with a quick crash course on the broader history of mammals. So mammals belong to a much larger group of animals called the synapsids. And this entire group includes every amniote tetrapod that's more closely related to modern mammals than to other groups, so reptiles and birds, and of course amphibians. And so synapsids have a very long evolutionary history, more than 320 million years, which extends way down into the Carboniferous period. And over that period of time, they've survived and seen many changes to the environment, including no fewer than 4 major mass extinctions. Now, for reference, throughout this talk, I'm going to be referring to a few what we call grades of evolutionary organization that characterize distinct steps in the synapsid story. And so the first grade that I'm going to refer to are these pelycosaurs. They're the earliest, the most primitive grade, and these superficially looked like modern reptiles. And they include such famous members as the sailback Dimetrodon. The next grade are the therapsids, and you might sometimes have heard these colloquially referred to as mammal-like reptiles. So they show a number of important anatomical advancements in the skull, in the jaws, and in the postcranial skeleton that puts them closer to the mammalian condition. Our next grade are the cynodonts, which show even more anatomical transformations, putting them closer to mammals. And cynodonts are basically as close as you can get to mammals without being one yourself. So, part one, reconstructing musculature and its evolution through time. How do we go about studying the muscles of extinct species when muscles typically don't preserve in the fossil record? Well, to do that, we rely on two lines of evidence. Firstly, we study what we call muscle scars. So these are telltale surface features left on the surface of the fossil bones that indicate where muscles once attached. And we can observe these same kinds of structures on the bones of modern animals today, where we know where the muscles once attached. And they can present a wide variety of manifestations. So we can see ridges, grooves, tubercles, pits, fluting, striations, longitudinal furrows, a great variety of manifestations. And we can also draw upon a comparative approach by studying the anatomy of modern animals. So drawing upon 2 centuries worth of literature data and observation, as well as undertaking our own novel dissections of fresh anatomical material. So to make sense of all these observations and to help guide our inferences, we bring all this data together in a phylogenetic context, an approach that's generally referred to as phylogenetic bracketing. Now, this requires 3 things. Firstly, a hypothesis of homology for a given muscle across all the species involved, both the modern species and our focal species of interest. Secondly, it requires a hypothesis of the phylogenetic interrelationships between all the species that we're making comparisons to. And lastly, it requires us to be able to recognize homologous osteological correlates of muscle attachment. So we need to be able to recognize that this particular osteological correlate of the muscle attachment in this species is evolutionarily continuous, it's homologous with this osteological correlate in this species. And so through this phylogenetic bracketing approach, if we can recognize homologous osteological correlates in our modern species that bracket our extinct species of interest, we can then recognize this condition in the most recent common ancestor of all these species, and then by default infer its presence in all the descendants of this most recent common ancestor, including our extinct species of interest. And so if we can then recognize the presence of a homologous osteological correlate in the extinct species, we can confidently infer the presence of that muscle, even though it's no longer preserved. And we can improve the precision of our inferences if we take into consideration data from other extinct species as well. And this can be particularly relevant if osteological correlates change in the way that they're expressed on the bones as we go through evolutionary time. Now, to provide a couple of examples of the kinds of insights we can gain from this approach, I'll walk through a few examples now. So first of all, we have the teres major. This is a muscle that is unique and distinctive to modern mammals, and it's a forelimb muscle. It runs from the scapula or the shoulder blade down to the back of the humerus or the upper arm. And this muscle typically leaves a distinctive scar on the back of the humerus called the teres tuberosity. Now we can recognize a comparable scar in many, many fossils. Often it's a linear ridge or a longitudinal tubercle on the back surface of the humerus. And we can trace this teres tuberosity all the way down to early cynodonts, about 240 million years ago. So far from being distinctive to just modern mammals, the teres major actually has very great antiquity to its history. Now, interestingly, a very similar arrangement is also observed on the humerus of a separate group of non-mammalian synapsids called the dicynodonts. And these were a herbivorous group that looked like a strange cross between a turtle and a hippopotamus. The interesting thing here is that dicynodonts are independently or separately evolved from cynodonts, which the latter of which gave rise to mammals. And so this means that a teres major muscle actually evolved independently, convergently in these 2 separate groups. For a second example, we'll look at the hind limb. And so we're going to focus on the biceps, or more generally, the hamstring muscles of the limb. So these run from the back of the pelvis down the back of the thigh, and they attach to the bones of the shank, so the tibia and the fibula. And they leave scars on these bones, especially the tibia. And so we can go looking in the fossil record to try and identify and trace out the history of this muscle attachment. And we can actually trace this for a very, very long period back through evolutionary history. So starting with modern mammals, we can find this scar in Mesozoic mammals and then into advanced cynodonts, into more basal cynodonts, then into therapsids like therocephalians and gorgonopsians and dicynodonts and even dinocephalians, down into pelycosaurs, and even outside of synapses into stem amniotes. So we can actually recognize this scar of attachment, this insertion on the tibia, way down for more than 300 million years of evolution. So this muscle attachment is extremely conserved over a very long period of time. Now we can also, I should also point out that this muscle attachment in many of these extinct non-mammalian synapsids has a very distally extensive insertion. So here I'm showing photographs of the tibia, the main bone of the shank, the shin bone, and you can see this scar of attachment, so it's a linear longitudinal furrow. It extends well down the length of the bone, sometimes into the distal quarter of the bone, so very close to the ankle joint. And what this means is that some of these hamstring muscles had a very distally extensive insertion. So these animals had very deep thighs and not much of a crook to the back of the knee. And so these kinds of observations and inferences start to force us to reevaluate our conception of what these extinct non-mammalian synapses once looked like as living animals. Now, we can look at individual muscle history, but we can also take a higher level approach and look at the evolution of limb musculature, considering all the muscles of the forelimb and hind together. And to do that, I undertook a phylogenetic analysis. So this is where I codified the presence and absence and manifestation of all the major muscles of the limbs, and I codified them for 33 operational taxonomic units, mostly at the family grade or higher. You don't need to worry about what each of these families or operational taxonomic units are. Just understand and appreciate that we have a detailed phylogenetic tree of the history of synapsids, and that allows us to start probing questions about how muscle evolution played out over their history. And we can use approaches like ancestral state reconstruction to understand and estimate the most likely pattern by which muscles changed on that stem lineage, that tree's backbone, as we go to modern mammals and to modern therians. Now, if we plot the number of character state changes against the node on that stem lineage, what we find is that far from being a linear or even or gradual pattern of anatomical transformation, we find that the history of limb muscle evolution, both in the forelimb and the hind limb, was quite complex and nonlinear, and it was punctuated by several instances with pulses of rapid anatomical transformation interspersed among periods of more quiescent and relatively low rates of change. And interestingly, we also observe that some of these pulses of major transformation are very late. They continue within the crown group of mammals. Some of these changes have only happened very recently. And so to summarize these results from part one, we can see that the distinctive musculature, the distinctive anatomy that characterizes modern mammals today is actually a unique mixture of very ancient as well as very recently evolved traits. And the overall history of limb muscle evolution was a complex and protracted and mosaic series. It wasn't a linear, gradual narrative. We've also identified some interesting instances of convergence between separate, only distantly related groups, which has important implications for higher level questions like deep homology. And these are things that still need to be investigated further in the future. Okay, on to part two. So with our improved understanding of limb muscle anatomy in extinct non-mammalian synapses, we can now use biomechanical models to probe and quantitatively explore questions about locomotor evolution and limb posture and limb function and how that's changed through time. So to do that, I use musculoskeletal models, which are essentially a collection of complex mathematical equations that relate all the cascades throughout the neuromusculoskeletal system. So we have equations that relate how excitation or neural signals from the central nervous system produce changes in activation and recruitment of limb muscles. We can then relate how this change in muscle recruitment interacts with the muscle fiber architecture, the internal structure of the muscles, to produce muscle forces, and then how these muscle forces pull on the bones to move the bones about joints ultimately producing whole animal movement. Now, to build these models, it's relatively straightforward for modern species. We need to acquire the geometry of the bones and the soft tissues, in this case the muscles, and we can do that through CT scanning of an intact carcass. Once we've got our geometries, we can port them across to dedicated modeling software like OpenSim, where we articulate the bones at virtual joints, and we can string up the muscles from origin to insertion to describe how their paths vary through 3D space and how this changes with changes in limbs configuration. We also need to parameterize our models. For instance, we need to assign the maximum contractile force or the maximum strength of each muscle. And we can do that by estimating these parameters from internal architecture of the muscles that we can study from dissections of fresh material. Now, for the extinct species, we follow a fairly similar process. Again, we need to digitize the geometry of the bones from CT scanning or laser scanning or photogrammetry of the fossils in museum collections, and then we digitally rearticulate them via virtual joints. Then we need to reconstruct the musculature. Drawing upon our observations of muscle scarring on the fossil bones, we can then build up what we often refer to as a muscle map, which describes graphically where all the muscles attach to every bone in the skeleton. So then we can rig up virtually these muscles from origin to insertion, describing how they pass over joints and encapsulating how muscle force is translated to limb motion throughout a limb's range of movement. Now, we can use these models to address a wide variety of questions. But here today, I'm going to focus on one question in particular, which is how much force could a limb apply against the external environment? Now, this is an important question because we know that a limb's maximal force-producing abilities is intricately linked and is a key determinant of locomotor performance in modern species. So we can use our models to calculate the maximum amount of force that can be applied on the environment in a given direction for all directions. And when we do that, we end up with a complex three-dimensional envelope that's called a feasible force space. So think of it as a force field that describes a limb's overall force-producing abilities, a metric of its performance. Now, we know from studies of modern species that a limb's force-producing ability can vary quite a bit with differences in limb posture. And so we also should be calculating a feasible force space across a range of postures. So here we did this for differences in limb flexion or crouch, so how extended or how crouched it was, as well as the different adduction angles. So adduction angle here is the angle between the proximal limb segment, so either the upper arm or the thigh, and the midline sagittal plane. And importantly, adduction angle is one way that we can measure how sprawled or how erect a given limb posture is. I should also point out that in this study, we only focused on the hind limb. And the reason being is that the forelimb, which is also involved in locomotion, has to be used for other ecologically relevant functions and behaviors as well, such as digging or holding onto food. So by focusing squarely on just the hind limb, we're hopefully going to get a signal that's much more faithfully reflective of what's going on in terms of just locomotion. Now, as with any modelling approach that's applied to extinct species, it's always a good idea to benchmark and validate your approach first with modern species where you know what results you should be expecting. So in our study, we benchmarked our feasible force space calculations with 5 modern species that phylogenetically and functionally bracket the synapsid sprawling to erect transition. So we have a sprawled tegu lizard, a salvator. We have an American alligator, somewhat semi-sprawled, semi-erect. We have the monotreme echidna, and we have 2 erect therians. We have the placental dog and the marsupial opossum. And so this is where our 5 modern species fall or sit on the phylogenetic tree. And then to this tree, we're going to add 8 extinct species that were chosen based on well-preserved and accessible fossil material. So these species are Ophiachodon, a relatively primitive pelycosaur from the early Permian, as well as Dimetrodon, one of those famous sailbacks. It's an advanced grade of pelycosaur. Then we've got a few therapsids. So Odenodon, one of these beaked herbivorous dicynodonts. You've got Lysonops, a carnivorous saber-toothed therapsid from the late Permian. And we have Regisaurus, a therocephalian from the earliest Triassic. Then we've got some cynodonts. So we have Mesitognathus from the middle Triassic, and teeny tiny Megazostrodon from the earliest Jurassic. Our last extinct species is Vincelestes, which is a stem therian. So it's a true mammal. It falls within the mammalian crown group, and it's more closely related to placentals and marsupials, but it falls outside of that therian crown group. So collectively, our species, the modern and extinct ones, capture all the different grades of evolution as we go along synapsid history. And collectively, they also capture much of that important anatomical transformation that took place on the line to modern therian mammals. So for each of our species, we calculate feasible force spaces across a range of postures. And then to look at the results, to look at limb performance, we can focus on a variety of different metrics. And here we're going to look at two aspects, which is the cardinal directions of force. So how much force is being produced up, down, forwards, backwards, lateral, and medially. And we can also look at the volume of that feasible force space as well, which gives us an overall metric of force producing ability. And so again, we can run an ancestral state reconstruction for these metrics. And we find that for several of these metrics, they tend to reach a maximum or a peak around about early cynodonts before they decrease back on the line to modern therians. So in some aspects, there was a transient increase in limb performance, which might have had implications for the kinds of postures that these extinct species used. However, we also find that the posterior force producing ability, so shown here in the green line, this tended to increase more or less monotonically on the line to modern therians. And so this suggests a progressive increase in ability for forwards acceleration as we go closer and closer to therians. A different way that we can look at these results is to boil everything down into a single simplified plot. So what I'm going to do here is on the x-axis, I'm going to plot the optimal adduction angle. This is the adduction angle at which a limb's force-producing ability is maximized. And we know from studies of modern species that this tends to correlate pretty closely with the postures that these modern species actually use in life. And on the y-axis, we're going to plot the Pearson correlation of a given species' force-producing profiles, compare that with the profile of the dog. So essentially, we're asking how dog-like or how therian-like is a given species' force-producing abilities. Now, if the transition from sprawling to erect limb postures in synapsids was a relatively linear, straightforward affair, we might expect a pattern like this, going from more sprawled and less therian to more erect and more therian. In reality, we get this pattern, which is a bit messy. And here I'm plotting on this yellow dot the ancestral state reconstruction, tracing out the most likely course of locomotor evolution. Now, clearly, this is not a simple straight line, a linear process. It's a bit all over the place. It's jumping back and forth like a pinball machine. Interestingly, we'll also note that of all the species, none of them approach the condition that we get into modern therian with the modern therians. So there's nothing that's showing a therian-like pattern of hind limb performance until we get to theria itself. Now, another way that we can distill these results is by running a cluster analysis on all the species. And again, if the transition from sprawling to erect limb postures was a simple, straightforward matter, we might expect a result like this, where increasingly derived or advanced synapsids show an increasing degree of similarity in their force-producing profiles compared to the modern therians. But instead, we get another jumbled up mess. And if you look carefully, you'll see that we recover two major clusters, a sprawling one and a non-sprawling one. And importantly, that stem therian Vincelestes falls in the sprawling cluster. So hopefully you can see that biomechanical modelling holds great promise in allowing us to probe locomotor function and performance and help to reconstruct how this could have changed through time. And we can see that the history of locomotor evolution in synapsids, far from being a linear or simple narrative, was quite complex and protracted. And importantly, erect locomotor function and erect locomotor posture, something that we tend to regard as a classical mammalian trait, seems to have evolved much later than previously thought, and it only typifies a restricted subset of all of mammalian evolution. More broadly, I hope today that I have shown you that the history of mammalian locomotor evolution is a complex and fascinatingly rich history, and we've still got many, many mysteries that we have yet to fully unpack. And hopefully they've also demonstrated the continuing value in studying old bones and combining that with new methodological techniques that can provide important illumination on some of our questions as we move into the future. And with that, I'll wrap up my talk. I'm very happy to take any questions, and thank you very much for your attention.
Thanks to you so much, Peter. That was a fascinating talk. A quick reminder to the audience that if you have questions, you can send them either directly in the chat if you don't want to be anonymous, or you can send them to the questions at Paleoprax host if you want to stay anonymous. You can also use the raise hand function. With that, we already received a few questions, so I'm going to drop those in the chat.
Okay, how do I bring up the chat from here? Do I need to...
Yeah, it's a bit tricky if you share your screen, but please keep sharing your screen if you can. I think on the side there should be a little button.
Okay, I see. You'd think after all these years of using Zoom, I'd figure it out by now.
I mean, they keep changing the layout. So yeah, so I've dropped it in the chat now. I'll also read it out. So this question asks, and now I disappeared it for myself. Yeah,
how common is it?
Yeah, how common is it for muscle scars to be preserved well in fossils? Does it require a special degree of preservation?
Yes and no. So often the degree in which muscle scars are preserved on fossil bones can actually vary with the group of animals under consideration. So in other words, different groups of animals preserve their muscle scars to different extents. And this is something that we can see in modern species as well. You can go to, for instance, horses and sheep and those kinds of animals. Their muscle scars are often very, very well preserved. You can very easily tell, oh, this is where the muscles attach. But you go to other groups of animals, for instance, lizards or crocodilians or turtles, only some of the muscles leave a distinctive scar of attachment on the bones. And it's no different when we go to the fossil record. So sometimes the variation is actually just a taxonomic, a species-specific variation. But also there is a requisite for generally good fossil preservation as well. If the fossils, looks like it's been hit by a car and it's flattened over and it's not great, generally speaking, you're not going to see as many. Maybe you'll still see some, but generally you're not going to see as many good muscle scars. But certainly when you do find a very well-preserved animal, if it's articulated or it's very nicely preserved, then yes, you have a much greater chance of seeing those muscle scars, particularly the finer scale, the finer, more subtle scars like the surface fluting and the ridges.
Okay, thank you for that very comprehensive answer. I think that makes total sense. Now we have a question in the chat from Adrian, who asks, often it is mentioned that erect locomotion has many advantages, such as directional force production, decoupling of breathing and walking. But can you think of trade-offs, like disadvantages for erect locomotion?
It's a great question. I greatly appreciate that question. Yes, in all cases, there's going to be a trade-off. Otherwise, why do we have animals that aren't erect, like lizards and salamanders? Why haven't they evolved erect posture? And so part of the answer to that question is we still don't know. It's still an active area of research. One aspect that seems fairly certain is that erect posture might provide these benefits that you've mentioned, but one disadvantage is that you're intrinsically less stable. So by that I mean, if you think of all the feet on the ground, whether you've got 2 feet or 4 feet, if you think of like drawing a convex hull, a polygon around your feet, that's what we tend to call the polygon of support. And in an erect animal, it's much smaller because the feet are closer together to the midline. And in a sprawled animal, for instance, like a lizard or a salamander, those feet are much further apart. And that polygon of support is a lot larger. And so the spacing of your feet changes how easy it is for you to tip over or to lose your balance. And so the evolution of erect posture certainly, almost certainly came with a trade-off of being intrinsically less stable. Does it actually mean that these animals were less stable in life? Well, maybe not, because maybe they might have at the same time evolved changes to their central nervous system, changes in neuromuscular coordination that actually kept pace with being able to handle greater instability. But yes, the shorter answer is yes, there's always trade-offs, because if there weren't, then everything would be evolving to a single common body plan.
Thank you so much. We actually had an anonymous question that is very similar to this. So I'm just going to drop it now and you can see if you want to add anything or not to the answer. What environmental conditions do you think might have pushed synapsids to either sprawling or erect postures?
Yeah, it's an excellent follow-up question. I think when we start thinking about the drivers that I alluded to in the beginning of my talk, the evolutionary drivers, whether they be environmental, physiological, or whatever, we can sometimes run the risk of getting sucked into looking for the answer, the one driver, the one reason why this great transformation in anatomy and function happened. The reality is the entire history of transformation in synapsids, this took place over 100 million years or more. I think you can have one environmental condition or one selective factor or one physiological reason that consistently drove that change for that that extended period of time. I think it's far more likely that there were multiple factors that, through maybe luck or contingency, happened to conspire in the right order at the right period of time that drove the evolution of erect postures. Because if you also think about it, if there are these environmental factors that are driving synapsids to acquiring an erect posture, well, why aren't they affecting the other animals in the environment at the same time? So synapsids and the reptiles, they both appeared, they both evolved in the same environments. They live side by side with each other for hundreds of millions of years. So what environmental conditions would selectively affect the synapsids, but not the reptiles? And so I think looking for those kinds of questions, we need to avoid looking for simplistic, this is the be all and end all that led to this postural shift taking place. I think it's a far more complex, far more nuanced scenario that would have led would have resulted in this this massive anatomical and functional change occurring.
Yeah, that makes sense. Great answer to a very complex question. Again, if you want to ask your question in the chat, that's also fine, but we still have some more anonymous questions. The next one says, great talk. How important is it to take into account ontogeny with these type of studies? Can you only use adult specimens? And then as a follow-up, are there studies that focus on differences in locomotion between juveniles and adults in extinct species?
This is another great question. And yeah, I think it depends on the question that you're actually asking. So we certainly know from studies of modern animals, experimental studies, that in certain species, there can be significant differences in anatomy and locomotor function as you go through a species ontogeny. As far as the questions that I was addressing in my talk, we try to, whenever we're selecting a fossil species or a fossil specimen to build our models on, we are generally trying to focus on a species that's adult, that represents what we think, our conception, what we think of as an adult representative of that taxon. Sometimes we have no choice. Sometimes there's only one specimen of that species in the entire world. And it's also sometimes difficult to actually tell with confidence, is this actually an adult or is it kind of a sub-adult? So there are those difficulties, but also in terms of the very broad-ranging questions that I'm asking and I was talking about in this presentation, you would like to think that differences between different stages of the same organism's ontogeny, so differences between, say, a juvenile and adult Dimetrodon, they'll be much, much less in comparison to the differences between species, between families, between different major grades of synapsid evolution. So in other words, I would expect to see that the differences between a juvenile and an adult Dimetrodon to be swamped out by the differences between an adult Dimetrodon and an adult Megazostrodon. And so in that kind of comparative context, I don't think ontogeny is that much of an issue, but it's not something that we should completely and always ignore. It depends on the question, I think.
Thank you, Peter. I'm just gonna get on with the next question, if you don't mind.
Sure.
Which says, fascinating talk. Could some of these mammalian type muscles have evolved more than once, or is that unlikely?
No, I think it's, at the end of the day, we are constrained by the available evidence that we have at our disposal. So we could find, for instance, a fossil tomorrow that forces a rethink on a particular muscle that we're looking at. And so, as I mentioned in the talk, with the dicynodonts and that teres tubercle and the teres major, there's evidence there that this particular muscle potentially evolved a very similar, maybe not necessarily identical, but a very similar manifestation in both the dicynodonts, which ultimately went extinct and gave no descendants, and the cynodonts, which gave rise to mammals. As far as other muscles are concerned, that's also a distinct likelihood, particularly those muscles where we don't have as good a handle on the osteological correlates. So, for instance, there are many muscles in the mammalian forearm, like the digital flexors and the extensors, that are distinctive for modern mammals, but they don't actually leave distinctive or recognizable muscle scars on the fossil bones. So when it comes to inferring and reconstructing the anatomy of the forearm in many of these extinct species, there's a much greater degree of uncertainty involved. And so that opens up the possibility for convergence and this repeated evolution of different muscle types in different groups of animals. And at the moment, we have no way of knowing, simply because we are limited by the available fossil and anatomical evidence that we have at our disposal.
Yes, I guess that remains a problem for everyone,
Yeah.
working with fossil material that we're never going to solve, I guess.
Well, I think that's also part of the reason why we're studying these animals in the first place, is because they are different, and they're not an easy, oh, I can solve that species is all worked out next. Because they are different, because they have no modern counterparts. That's part of the intrinsic fascination that we have with them, that they are these unique relics, these unique elements of a time gone by. And so it's kind of a double-edged sword in that respect.
Oh, definitely true. So far, I have one question left in my queue. So friendly reminder to everyone, if you have any more questions, please send them sooner than later. And this one asks, how about the role of tendons? Can you get information on them from muscle scars as well?
Yes. So often tendons tend to leave more concentrated and more rugose scars on the bones, whereas ones that have muscles that have broader fleshy attachments, they tend to leave sometimes a more subtle surface scar. So, for instance, a tuberosity or a very distinct bump or process is more likely associated with a tendinous type of insertion as opposed to a broad area of fluting or ridging. When it comes to modeling tendons in our computational biomechanical models, we can certainly take that into account. I didn't do it in the modeling that I showed today, but we can accommodate the influence of tendons. So it's not just a muscle, but we can have a tendon that's in series with that muscle, and that tendon can stretch passively as more force is applied to it. So there are certainly there are ways that we can incorporate tendons into our reconstructions of the animals, and also our biomechanical analyses of their posture and their locomotion.
Oh, that's very cool to know. Yeah, those were the questions I had in the queue. So I'm waiting a few more seconds to see if there's any other trickling in. In the meantime, I again want to thank you for a talk and for a great Q&A. I'm really fascinated. I'm not a paleontologist, or I don't know how you would describe yourself, someone who works
Kind of do a bit of
with
everything, I
fossils,
guess.
but
I
yeah,
greatly
super
appreciate the
interesting.
opportunity, and I greatly appreciate all these questions. Every single one of these questions are great. Not only does it show that I've actually communicated my ideas and my results to a nice broad audience, but that people are actually seeing, this is an aspect where perhaps this is the next step to take the research. So it's great to see all these questions and the feedback. It's very much appreciated.
I'm very happy that you enjoyed it too. It seems that there's no more questions for now, so I am going to share some information and introduce next week's speaker before we move into the tea time. So again, thank you very much, Peter, for your talk. It would be greatly appreciated to all the audience members. Also, thank you for being here and thank you for your questions. If you could fill out the weekly feedback form, which you can find in the chat. And also please consider joining our steering committee or letting someone know who you think might be interested in that. Then yeah, next week, October 28th, we are back. Note that this is for Europe at least, a shift to daylight savings. So this will be 16 UTC. Please check whether this is the same time for you or whether this is an hour later or earlier now. And then we will be joined by Xianyi Lu from the Utrecht University in the Netherlands, who will be talking about stratigraphic modeling and more info about that coming soon. Then, as I mentioned earlier, Peter has agreed to stay for tea time. So again, for everyone who's new here, tea time is just an informal chat with today's speaker where we turn off everyone can turn on their cameras, we stop the recording, and we can just have a chat or just say hello. But before we do that, we want to give everyone a quick break, especially our speaker. So we'll have a 2-minute break. And after that, please come back if you're interested. If I won't see you, then hope you have a great rest of your day and hopefully see you till next week.